All right, let's carry on. So we now start a kind of new chapter here because we've been physicists up to now, and for a few minutes at least, we will be mathematicians. We're going to make like very concrete statements, very solid, reliable statements about what we can do here. And then once we've been mathematicians for a little bit, we will go back to being physicists because we're going to start finding tricks to approximate these difficult solutions that we're trying to find. Okay, and here we are going to focus on the Laplace equation. Okay, so our Laplace equation is really the kind of simplest equation we've seen up to now, which is kind of fortunate because it's also the one that we'll discuss the most about in the coming little bit. Okay, so what I'm going to do is do a short discussion about some basic properties of the Laplace equation, and then we will state some fundamental theorems for what these things are. So I think it's going to take like maybe 20-25 minutes to do the physicist bit here to discuss some basic properties there, and then we'll do our mathematics stuff. Okay, so let's just look at very simple starting points. So one dimension. So what is the Laplace equation in one dimension? It just tells you that the second derivative of your phi, which is now a function of a single variable x, it tells you that the function has no curvature. Second derivative is 0. And therefore, you can immediately write the most general solution to the Laplace equation in one dimension, which is just a linear function, ax plus b, where a and b are just numbers. Okay, there is nothing else. Okay, so maybe some fun properties or fun useful facts. The solution to the Laplace equation, at least in 1D, has a property that we can call balance. And what we mean by this is that, in general, if I take an evaluation point x here, and I imagine another evaluation point here, x plus epsilon, and another evaluation point x minus epsilon, then for any epsilon and any x, the value of the function at x is the average of the value of the function at x minus epsilon and x plus epsilon. Okay, so 5x is equal to 1/2 phi of x minus epsilon plus phi at x plus epsilon. Okay, so at this stage, for you, this is just a trivial consequence of the linearity of the solution for that 1D case that we have here. Okay, and the other thing that we can obviously read from this is that it has no extrema. When you're usually doing optimization, you're trying to find a solution to a set of equations. You try to find a minimum or a maximum, a saddle point or anything like that. These points are characterized by second derivatives, vanishing like this. Here, you're kind of screwed because it's 0 everywhere. Okay, so the function has absolutely no curvature. So there's no, notion of a minimum point or anything. There are no extrema to the solution of the Laplace equation in 1D. Okay, so I hope this is quite clear. So in order to fix the solution, what do I need? I need information. And this information can come from various sources. Okay, so to fix the solution. Is it working? So to fix the solution, you would need to tell me information that is equivalent to telling me what these coefficients A and B are. And one possibility is for you to give me some boundary conditions. So let me get you used to this boundary conditions, because I'll write that very often. Okay, so for example, you could give me the value of phi at both ends. Okay, so here assuming boundaries. Okay, so let's say I've got a finite interval, yeah, segment, and I want you to give me the solution of the Laplace equation in this segment. Then you say, fine, tell me some information. And this information can be, I tell you that the value of phi at the left boundary is so, and the value of phi at the other boundary is so. Two informations. For any value that you give me here for these things, I will be able to find parameters A and B fitting that fitting those conditions and giving me a unique solution to the Laplace question. No. So phi at left is equal to, call it phi L, which is a constant, and then phi at the right is equal to some other number of phi R, but numbers of your choosing, independent of each other. Okay, and it's manifestly clear that whatever numbers you give me are guaranteed to give me a unique solution. There's only one choice of A and B that gives me the phi here. And therefore, under those circumstances, the solution to the Laplace equation in one dimension is, it exists and it's unique. Okay, existence is manifest, uniqueness is guaranteed. You could also give me phi and d phi dx at one end. Okay. You could also give me phi at one end and d phi dx at the other end. Okay. At opposite ends. Okay, these would all be possibilities that would allow me to fit the parameters A and B in there. Okay, and there's a remaining case. If you give me d phi dx at both ends, then either you're giving me something that doesn't work, because if you tell me d phi dx is that number here and that different number here, then I cannot fit this, right? Because d phi dx is throughout just A. I got one fitting parameter here. So if you give me d phi dx at both ends, you're either giving me something inconsistent from which I cannot find a solution, or you're giving me twice the same information, which means I'm still missing one piece of information. So that doesn't work. Okay, but the other cases work. So that's the first thing. Okay, so these are the simple statements we can make. Okay, very simple. So let's now move on to more complicated cases. Let's now do 2 dimensions. So in this case, I will have a function phi of, call it x and y, whose Laplacian in 2D vanishes. Okay, so this is our Laplace equation in 2D. I call it in the notes, it's just Lap 2D. The other one was Lap 1D. Okay, so here you see, you start having some interesting non-constant, non-necessarily linear behavior in there. And there's a lot of discussion to be had about the shape of these possible solutions. For example, if you think of a drum in space, then the equation that is obeyed by the membrane is precisely this. Okay, and what does that mean? So maybe a little bit of interpretation of what these things are. How would you interpret the curvature in the x direction? Let's say you've got an elastic membrane. Okay, then if your membrane is curved, let's call this the x direction. Let's say that it's got a positive curvature in the x direction. If this is like a rubber band like membrane, then the point which is at the bottom of this curvature is going to be pulled up. Okay? Because it's curved, the neighbors want to, therefore the force kind of adds up to something positive. However, the thing could be equilibrated if in the other direction it was being pulled down. Okay, so now imagine taking a piece of elastic cloth, right? And imagine taking the edges and shifting them. You get a membrane that has a shape. This shape is a solution to the 2D Laplace equation. Because if it was not, it would mean that there would be a force remaining on the point, and the point will move in response to the force until the force is zero. So the way you visualize a solution to a two-dimensional Laplace equation is by thinking about such a membrane that has boundary conditions set by, shifting the height of the edges, and then the membrane adapts to this. But everywhere you look, because the membrane is not moving anymore, it means that the force on that point is zero. So the force on that point is going to be pulled down maybe in that direction, but it's going to be pulled up in that direction, resulting in zero force. Okay, so that's what these things are. So in a kind of equilibrated membrane with boundaries twisted up and down here and there, that's what describes this membrane is the solution to this 2D Laplace equation. Now, you understand by now that these solutions in general are quite complicated, right? Complicated functions and whatnot. So we have to get back to study that. However, it still has the balance property, meaning that the value of the function of the solution of the Laplace equation at a certain point is just going to be equal to, let me write it like this. dl of phi at, how could I write it? R plus L dl. So this is, I have a point and I have a circle of radius r centered at the point xy, and my little L is really just integrating this. Okay, you see what it means? I just take my evaluation point, I define a little circle around it, and I average the value of the function along this little circle, and that's the value of the function in the middle of the circle. Okay, what if I take a step left or right, and I average over all possible steps, in total, I don't know. Okay, so that's a very important possibility here. And of course, the other no extrema condition also holds. Okay, so this holds and this also holds. So what does that mean? It means indeed that there, manifestly, there's no point xy that is such that the curvature in all directions is positive. If it's positive in a certain direction, it has to be negative in a neighboring direction in order to make sure that the Laplace equation is fulfilled. Okay, so that's the thing. So that's for 2D. And then for 3D, you'll have guessed it, 3 dimensions. Well, now it's the same thing. So we'll use our more economical notation. So the full Laplacian of phi of r is equal to 0. And here again, here again, we'll have exactly the same balance condition on this, except that now we want to integrate over a spherical shell around a certain point. So my function at r, if it is solution to the Laplace equation, is equal to its integral over a shell of radius r. So I do the full integral over the closed surface, but now with this dA, two-dimensional object of this, of phi of, you know, the point plus the, how can I call it? Yeah, A, you see, it's just the differential surface element over this thing. Maybe I'll just call this r prime. Okay, you see what I mean? I've got a point r, I've got a shell around it, and I'm integrating over these little dA, which are situated at these points r prime on the shell surrounding r. Okay, so again, this is the same thing, balance and no extrema. In the online notes, I give you 2 proofs of this balance theorem. I give you a physicist's proof and a really formal proof. I invite you to look at these things because they're enlightening mathematically, but also physically, because there's a physical consequence to that thing, which is called Earnshaw's theorem. And Earnshaw's theorem, because it's just like a manifestation of this no extremum condition here, it just says that there does not exist an electrostatic potential. Nice. Right? Giving a stable equilibrium. Okay. Electrostatic fields, I'll just say it and then come back to it. Electrostatic fields originate from potentials which are solutions to the Laplace equation in 3 dimensions or in 2 dimensions and whatnot. These solutions have no extrema. It means that in the lab, however hard you fight with, you know, placing charges left, right, and center, nice configurations, rings, plaquettes, whatever, irrespective of what you do, you will never be able to hold a charge in an equilibrium position. Okay? Which is kind of funny because I don't know about you, but the way I experience, you know, matter and stuff, it seems to be in equilibrium. But why? How can it be that we have crystal lattices if surely the atoms are held in place by electrostatic forces? And if they are not, you know, what does? So you see, you can think about that. I asked you the first time, how do you sleep at night? And I repeat this question here and now. Knowing Earnshaw's theorem, you know, how will you sleep tonight? That's the big question. Well, equivalent, because we're talking about solutions to the Laplace equation, therefore we're looking at phi, but of course the physical consequence of it is through the electric field. And the fact that the potential itself does not have an extremum means that essentially everywhere in space like that, there's going to be a direction of the field that takes you, away from that point. Okay, so there's no way to hold it. Yes. Because if I wanted to have a stable equilibrium, I would need at that point in space for my force to be zero on the charged particle. And in order for the force to be zero, the field has to be zero. And also, in order for it to be a stable equilibrium, I would need any displacement away from that point to give me a restoring force, namely a force directed back to my origin of displacement. So if I look at the change of the force as I move away, I'm looking at the gradient of E, essentially. I'm looking at the way phi second derivative changes. And what that tells me is that if I have a point with zero force, that's all very well, but if I move away from it, the restoring force will not always be back towards the point. There will be directions where I will have a tendency to fall back. Think again about our two-dimensional membrane. Membrane is shaped like this if I do a cross-section like this, but it's shaped like this. I'm like this. In this direction, I've got a good restoring force, but if I move away from this, I go away. Okay, so that's what it means. And this works in 3 dimensions as well, right? So if you have like, you've heard maybe about magnetic confinement bottles and things like that. You know that scientists all over the place, even here, they hold atoms confined in tiny magnetic traps. So how does that work? Yeah, exactly. Yeah, so you cannot do it statically. So it's not that you're holding them steady, it's that you're kicking them back continuously to where they were, which is not the same thing. Okay, so that's a very important thing. Now, so that's the kind of very, very important aspect of it. Okay, so now what I would like to do is leave you with kind of mathematical statements about this on which we will build next time. Okay, so I want to be a little bit formal here. So these are just properties of the solutions of Laplace equation.